Today we're going to look at finding the volume of solid objects, geometric solids, that have what we call uniform cross sections. So the easiest way to think about this is if we think about something like a cone, I'll draw a cone here that's kind of oriented horizontally. If I were to slice through this cone vertically at any place along here, regardless of where I slice through it and we open it up and look at it, the faces that we're looking at are going to be circles. So this has circular cross sections. If you think about a square pyramid, no matter how you slice it, as long as you slice it parallel to the base, it's going to have square cross sections. If you think about a rectangular prism, let's say we have a rectangular prism here. Depending on which direction we slice it, let's say we slice it, perfectly horizontally through it, we should be getting rectangular cross sections. And based on how I've drawn this, if I called this a square over here, if I sliced it perfectly vertically, we should be getting square cross sections. So that's what we're going to be looking at. We're going to be, though, looking at some slightly more irregular geometric solids, where the base of the solid isn't going to be something like a circle or a square or a rectangle, but it's going to be a function graphed in the coordinate plane. And so there's going to be a couple of rules that we're going to need to follow. The first is if we are looking at cross sections cut perpendicular to the x-axis, our integral that we're going to set up is going to have to be done in terms of x. And if we're looking at cross sections cut perpendicular to the y-axis, we're going to have to use y as our variable. And then we're going to just go in, find our limits of integration, find a formula for the area of each of the cross sections in generic terms, and then integrate across our entire region. And that's the whole basic idea of what we're going to look at here. We're going to start with this one. We've got the base of a solid is the region between the curve y equals 2 root sine x, which looks about something like that, and the x-axis. So we're talking about this region right here is the region we're talking about. It's going to be the base of our solid. And then coming out of that, coming straight out of the screen at you, is going to be the geometric solid. And if we were to slice it perpendicular to the x-axis, no matter how we did that, we'd be looking at faces that were squares when we opened it up. So I'm going to just do my best to draw some, little squares sort of protruding out of here. Imagine that we have, at the top here, we've got the biggest possible square. Down here at the ends, we've got real small squares. Right? And these squares are protruding straight out of the board at you, or out of the screen at you. If you slice it down and open it up, that's what you see is a bunch of squares, right? And we're thinking that we're slicing this thing into an infinite number of little squares along here that have an infinitesimally small thickness to them in the x direction. So each of these has a thickness of dx. What we're going to do is we're going to find the area of the face of one of these, the area of the square itself, multiply it by its thickness, in this case, dx, and then we're going to integrate across the entire region. So in order to find the area of that face, we got to think about what one of the side lengths is, right? Because we know that the area of a square is going to be the side length squared. And if this is the side length, we'll need to figure out what that is in terms of our variable x. And so regardless of which square we're talking about, we need a generic formula for that area, right? Because we can't just use s squared. We can't do an integral of s squared dx. That's not a thing. We can't do that. And speaking of that, since we're getting this out here, we're going to integrate from 0 to where this hits the x-axis over here, which is pi. But we can't do s squared dx. So we have to think about s is the same as y, right? This value in the y direction. And, well, y doesn't work either, but y is equal to 2 root sine x. So we're going to turn this into an integral from 0 to pi of 2 root sine x squared dx, or effectively 4 sine x, and I'll pull the 4 outside the integral, so we'll do 4 times the integral from 0 to pi of sine x dx, and then we'll integrate, giving us the integral sign is negative cosine, so it's going to be 4 times negative cosine x from 0 to pi. And the cosine of pi is -1, so negative 1 is positive 1. And then the cosine of 0 is 1, so we have 1 minus -1, effectively giving us 8 units cubed here for our volume. So our process here was sketch the region, sketch the cross sections, find a formula for the area of the cross section in generic terms, make sure we put it in the same variable as the thickness, and then throw it all inside of an integral and integrate. So we'll do another quick one here that's going to be almost exactly the same. We're still looking at the curve 2 root sine x from 0 to pi. But this time it says the cross sections, which are cut perpendicularly to the x-axis, are equilateral triangles, which means protruding out from your screen, no matter how I slice this, is a bunch of equilateral triangles. Real small ones down at the ends and bigger ones up at the top there. And so it's going to be really helpful to know the formula for an equilateral triangle's area. You should just know this formula. You can find it really easily using a little bit of right triangle trig with an equilateral triangle. I'm kind of drawing height down the middle of it, but if you just know it, it's s squared root 3 over 4. And we know that s, our side length, s is just equal to y, which is 2 root sine x. So effectively, when we put that in here, we end up getting 2 root sine x squared, which is 4 sine x, which will cancel with the 4 in the denominator. So we just have root 3 sine x. So we're now looking at an integral of root 3 from 0 to pi, root 3 times sine x dx. We just did that integral, except with a different constant out in the front. That was negative cosine x. And since we just evaluated that, we won't have to worry too much about that. Well, that came out to be 1 minus -1 inside of there, which gives us 2 root 3 units cubed. So hopefully not too terrible. The next one we're going to look at is a paperweight with its base that is the shape of the region between the x-axis and one arch of 2 sine x. And this time we're going to have cross sections which are perpendicular to the x-axis, which are semicircles. So first we'll sketch our function. One arch of 2 sine x looks about the same as what we did before. And we know that 2 sine x equals 0 at x equals 0 and x equals pi. So this will be pi and this will be 0 over here. And that'll be the ends of our interval for our integral. Those will be our limits of integration. With an integral from 0 to pi that we're going to be working on here. And our cross sections are semicircles. So I'm just going to draw one semicircle this time. But we have a bunch of them, an infinite number of them, in fact, because we're slicing this an infinite number of times. And the thickness of this is infinitesimally small in the x direction. The thickness of dx. And we know that the area of a semicircle is 1/2 pi r squared. And a really common mistake that people make here is that they just go in and equate r as y, 2 sine x. But that's not the case. So please make sure you do not do that, right? Our diameter of our semicircle is equal to y, which means that y is equal to 2r, or r is equal to y over 2, which in this case is 2 sine x over 2, or just sine x. So r is sine x. So our area just ends up being 1/2 pi sine squared x. So this here is a very common mistake on semicircles. So make sure you don't make that mistake. So 1/2 pi is just a constant, so I'll put that out in front. And now we've got sine squared x dx inside of our integral. And the easiest way for us to integrate sine squared x is to use the power reducing trig identity for sine squared, which you should know. If you don't know that, make sure you go back, find that, and memorize it. But it is 1/2 of 1 minus cosine of 2x. And so now we can pull out the 1/2 if we want to, which gives us pi over 4. And then the integral of 1 is x. And the integral of cosine 2x is just a basic u sub for 2x, one of these ones that you should be doing in your head by now. It's x minus 1/2 sine 2x. And we'll just evaluate from 0 to pi, which gives us pi over 4 times pi minus 1/2 of the sine of 2 pi. And we know the sine of 2 pi is 0, so that's pi minus 0. And then when we plug 0 into this, we get 0 minus 0. So effectively, our final answer is pi squared over 4 units cubed. So very helpful trig identity to know, the power reducing ones for sine squared and cosine squared especially. This time we're looking at the base of a solid, which is the region between the curve y equals x squared and y equals 4. So just gonna sketch this. There's y equals x squared and there's y equals 4. A couple of pretty basic graphs. So the region we're talking about is this region right here, in between the two functions we've got. We've got cross sections this time which are perpendicular to the y-axis. So the first thing we should read into that is we see it's perpendicular to the y-axis. We want to make sure that we do this all in terms of y. And we've got rectangle cross sections where the length is twice the width, and the width is this side stretching across the region. So here's a rectangular cross section protruding out from the screen there, where here's our width and here's our length, which is twice the width. And so we should very easily be able to see that the area of this cross section is 2w squared, because we've got w times 2w for our rectangle. But we can't integrate 2w squared dy, right, because the thickness of this cross section here is dy. It's infinitely small in the y direction. So we have to find a way to put this into terms of y. Now, to do that, we're going to first have to put w in terms of x, right? The length of w is twice this length right here. And this length is just a distance in the coordinate plane from the y-axis going to the right, which can always be defined as x. And since this is a symmetric function across the y-axis, it's an even function, the total width is going to be equal to 2x. So if we replace w with 2x, we've now got 2 times 2x squared, which comes out to be 8x squared. And then, because we need to turn it into terms of y, we'll look up here that y is equal to x squared, and we'll replace that x squared with a y. And so now our integral, which is from 0, the lower limit of this region, to 4, the upper limit of this region, should become the integral from 0 to 4 of 8, or 8 of those integrals of y dy. And now it's a really simple integration. 8 times y squared over 2 from 0 to 4 gives us 8 times 8 minus 0, or 64 units cubed. So just make sure that when you are working through a volume problem with uniform cross sections, and it says that we're perpendicular to the y-axis, we have to do the problem all in terms of y. So let's do one more. This will be the last one we do here. And it's going to be another one that's done in terms of y. So the base of our solid is the circle x squared plus y squared equals 1. And we've got cross sections perpendicular to the y-axis from y equals -1 to y equals +1, which are isosceles right triangles with one leg stretching across the base. So there's the leg, there's the other leg, and there is the isosceles right triangle. And we could draw as many of these in here as we want. There are an infinite number of tiny little slices of these. If you decided to draw them this way, there's absolutely nothing wrong with that. The answer will be exactly the same. It won't change the problem at all. Chosen for it. So since these are perpendicular to the y-axis, we know that the thickness is dy, which means that when we integrate from -1 to 1, the lowest point, -1, to the highest point, +1, we should be doing this all in terms of y. And the area of one of these isosceles right triangles is just 1/2 the base times the height. Well, since they're isosceles right triangles, the base and the height are both the same. We'll just call them L, or leg. And this is 1/2 L squared. So we can't integrate 1/2 L squared dy. So we'll have to write L in terms of y. In order to do that, though, we'll first write it in terms of x, because it's a distance in the x direction to begin with. In fact, this distance is x, the distance from the y-axis going over to some point on the circle. And since the circle is symmetric, this is also x, meaning that L is equal to 2x. So 1/2 L squared is actually equal to 1/2 of 2x squared, which should be 2x squared, right? 4x squared over 2. And then we need to figure out what x squared is equal to. Well, we can look right back up here to our original equation where x squared plus y squared is equal to 1, and see that x squared is equal to 1 minus y squared. And so this integral is now going to become two integrals from -1 to 1 of 1 minus y squared dy. And so we'll just do 2 times y minus y cubed over 3 from -1 to 1, which gives us 2 times 1 minus 1/3, when we plug in +1, and then minus -1 plus 1/3, when we plug in -1, which gives us 2 times 2/3 minus -2/3, or 2 times 4/3, or our final answer of 8/3 units cubed. And that's the whole idea of finding the volume of geometric solids with uniform cross sections. We're going to use this basic idea in the next lecture when we talk about solids of revolution, where we're going to have geometric solids in the coordinate plane here that are created by revolving a region around the x-axis or the y-axis or some other horizontal and vertical line. And so that's our next major topic for this unit on applications of integration. And we'll get to that next time. And that's it for today.